Hello guys, welcome to this video editorial of a problem from November Long Challenge. So I'm Istasis Mishra. I'm a fourth year undergrad at IIIT Hyderabad. I've been to ICPC regionals twice and I've also represented India in IOI 2018. So without any further ado, I'll just get right into the editorial. So this problem is problem 9 from the November Long Challenge. The name is functional array. Okay. So let's just get into understanding the problem statement. So the first para actually tells you what a functional array means in this context. The second para is actually the problem statement. So what does a functional array mean? Okay. So yeah, a functional array of A, we call it FA. Okay. So if A is something like 2, 3, 9, 11, okay, the functional array will be the difference of the adjacent elements. Okay. So in short, f of AI will be equals AI plus 1 minus AI. So naturally you can understand that if the size of A is n, the size of f of A will be n minus 1. So 1 less than the size of the original array. So what will be the functional array of A in this case, right? So 3 minus 2, 1, 9 minus 3, 6, 11 minus 9, 2. Okay. So this is the definition of functional array. Now the problem statement. You are given two arrays B of size n and Z of size m. Okay. Now you have to print yes or no based on if an array A exists or not. So this A must fulfill two criteria. Okay. The first one is B must be a subsequence of A. So B must be a subsequence of A, right? And the second criteria is f of A must be a subsequence of Z. So yeah, I understand that these two criterias are kind of interrelated in the way that it's a bit difficult to understand what it means. Okay. So first let's understand what a subsequence means. Okay. B will be a subsequence of A if, so let's say B is something like 2, 3. Okay. So if B is 2, 3, then A will look something like, there will be some elements, then 2, then some elements, then 3, then some elements, right? This is how your A should look like. Okay. This means that B is a subsequence of A, or A is a super sequence of B. Okay. So similarly, f of A must be a subsequence of Z. You just have to print yes or no based on if such an array A exists. You don't actually need to print the array. Okay. This is the problem that we have at hand. So how do you go about solving it? Few observations we can make. One of the observations that I personally came up with when trying to solve this problem, the first thing that people think of is about the size of the arrays, right? First, let's look at the constraints properly. Okay. So the last four constraints are the most important ones. Those are the actual elements of B and Z are always non-negative, so greater than equal 0. Sum of n over all test cases 10 power 5, sum of m over all test cases 10 power 5. So you can assume that the size of B and the size of Z will be less than equals 10 power 5. Each of the elements will also be less than equals 10 power 5. Okay. So these four are the most important constraints here. So first observation that I came up with was something like B is a subsequence of A. So size of A will be less than equals n, right? N is the size of B. The opposite actually. The size of B will be less than equals to the size of A, right? And similarly, the size of f of A will be less than equals to the size of Z. So this is one observation. Doesn't really help much, right? This is an observation, but doesn't really help. So yeah, if B is 2, 3, so this is actually the first test case that we have at hand. B is 2, 3 and Z is 1, 1. So what is a possible A for this? The first test case explanation says 1, 2, 3, right? 1, 2, 3. What will f of A be? 1, 1, right? So here is 1, 2, is B a subsequence of A? 2, 3 is here, 2, 3 is here. So B is a subsequence of A, right? So when I said that like there must be some elements between 2, 3, it can be no elements also, right? There don't have to be elements between 2, 3 for a subsequence to be a subsequence. So B is a subsequence of A. And is f of A a subsequence of Z? Both are 1, 1, right? Both are equal. So f of A is a subsequence of Z. So this is a valid A for this B and Z, right? But the thing is, here the explanation is kind of tricking you. In what way? Because this is not the only possible A that is viable, right? Think about some more A's. So pause the video here. Try to see if there are more possible A's which satisfy the two criteria for this given B and Z. What if A is equal to 2, 3? Is B a subsequence of A? It is, right? And what will f of A look like? F of A will look like just 1. And is f of A a subsequence of Z? It is. So this is another possible A. And this will be the A that our algorithm will be finding, not this 1, 2, 3, 1. Okay. So what observations can we make now? One observation is that, so I'll just take a random B to prove a point, right? So I'll assume the size of B is 2 for now. Okay. So let's say it's 1, 6. One more observation that we can make that I did not cover yet is, look at Z. Okay, since f of A is a subsequence of Z, that means that every element in f of A must be in Z, right? Every element of fa must be inside Z because fa is a subsequence of Z, right? So f of A cannot contain any number, any integer that is not inside Z, right? And what is the minimum value of Z? It's 0, right? So Z will be greater than equal 0. If Z is greater than equal 0, that means that our A, so that means f of A, every element in f of A is greater than equal 0. And what is f of A? A difference array, right? Difference of the adjacent elements. If the difference of adjacent elements is greater than 0, what does that imply about the array A? So A must be non-decreasing, right? It cannot be decreasing, right? If A was something like 3, 2, then our FA will become -1. But -1 cannot be inside Z because of the constraints. So so A will be non-decreasing. And B is a subsequence of A. So B will not contain any element that is not in A, right? So if A is increasing or non-decreasing, then B must also be non-decreasing. So right off the bat, this is one case that we can handle. If B is not non-decreasing, so if B is decreasing, that means not decreasing, like if B is like 1, 2, 1, if this is B, then the answer is no, right? 1, 2, 1 is not possible. It must be non-decreasing. Okay. So assume that B is non-decreasing, right? What after that? So one thing we can see is that A will be equal to, let's say 1, 2, 4, 6, right? what will f of a look like? Let's calculate f of a for this a, right? It will be 2 minus 1, 1, 4 minus 2, 2, 6 minus 4, 2, right? This is our f of a. Try to add these elements. What is 6 minus 1? 5. What is sum of all the elements here? 5, right? Why is this happening? Why is the sum of all the elements here equal to the difference of the two elements in B? So think about it, okay? So let me just write it for a general array so that it makes more sense. So A will be equal to some elements 1, some elements 6, then some elements, and it will end. Okay. So assume 1 occurs at index P and 6 occurs at index Q. Okay. Let's sum up all the elements from P to Q minus 1. Actually, in f of A. F of A, let's sum up all the elements till P to Q minus 1. Okay, that is what happened last time, right? From P to Q minus 1, we summed up all the elements. So summation of I equals P to Q minus 1 of f of AI, right? And that will f of, what is f of AI? What is f of AI? F of AI is AI plus 1 minus AI. Now think about it. So if I is equal to P, it will be, so f of AP will be equal to what? F of P plus 1 minus A of P, right? Now f of P plus 1 will be equal to A of P plus 2 minus A of P plus 1, right? F of A P plus 2 will be equals A P plus 3 minus P plus 2, right? Something like that. And f of A Q minus 1 will be equals what? A of Q minus A of Q minus 1. Now add these up. Add these up. This is equal to this sum. The left side of the equal to signs, if you add this, that will be equal to this value, right? That is exactly what we're trying to find. On the right hand side, you'll see this and this cancels, right? This and this cancels. So it's kind of a telescopic sum, right? So it's A of Q minus A of P. So this is equals A of Q minus A of P. What is A of Q minus A of P? A of Q is B of A of P is B of 0, and A of Q is B of 1. So that is equals B of 0 minus B of 1. This is if n is equal to 2. Okay, I'm only considering the case of n equals 2 now. Okay, and since f of A has this continuous subarray of some of sum equals B of 0, sorry, B of 1 minus B of 0. B of 1 minus B of 0, right? Z, so f of A is a subsequence of Z. FA is a subsequence of Z, right? So there must be a subsequence of Z that has sum equals to B of 1 minus B of 0. If Z is an array, there must be a subsequence of this array so that the sum of that subsequence is B of 1 minus B of 0, right? In this case, in our example case, in this case, 3 minus 2 is 1. Is there a subsequence that is equal to 1, right? There is. Any this subsequence and this subsequence, both are 1s, right? So that is why our f of a looks like 1, and that means a will look like 2 3, right? So we are trying to find a subsequence of a sequence of a list such of a specific sum. How do you do that? That is just 0 1 knapsack, right? Right? Let's look at the problem of 0 1 knapsack. Okay, what does it mean? What does 0 1 knapsack mean? So you have a list of items, and you just want to see if they can sum up to a specific sum, right? So you put all the items of a specific, so each item will have a weight, right? I'm talking about knapsack now. This is not related to the actual problem at all. So each item has a weight and some profit, right? These weights must sum up to the capacity, and we have to maximize the price. The cost of the items that we have taken, we have to maximize that. So here there is no cost. All the items have the same capacity. We just have to check if it is possible to make a specific sum, like if it is possible to take some items of specific weights to get to the maximum capacity C, right? So 0 1 knapsack, by solving 0 1 knapsack, we can very easily check if there is a subsequence of Z that sum up to a specific sum, which is B1 minus B0, right? And their complexity will be O of max multiplied by M, right? Max is the maximum difference of two elements in B, which is up to 10 power 5. So 10 power 5 into 10 power 5 will not pass, right? So there is a way to implement knapsack using a bit set. And if you use a bit set, it will be this value divided by 32. And that will pass, right? That will just barely pass. So you have to implement 0 1 knapsack using a bit set, and then your complexity will be something like the maximum value that you need to make multiplied by M divided by 32, right? But this is for n equals 2, right? This is only for n equals 2. What if B has more elements? So instead of 1 6, let's say it is 1 6 11. What now? So try to extend this idea now. So now A will look like what? Some elements 1, some elements 6, some elements 11, and then finally some elements, right? The same idea can be just extended. So instead of, so there will exist some other indexes such that they equal to B of 2 minus B of 1, right? So, and there will be a subsequence of Z that equal to B of 2 minus B of 1. So you have to partition Z now. There will be a subsequence here that is that has sum equals to B of 1 minus B of 0, and there will be a subsequence here such that their sum is B of 2 minus B of 1, right? So overall the solution is to partition the sets in some way into n minus 1 sequences. Partition the sequence Z into n minus 1 sequences. In each partition you'll find a sum, you'll find a subsequence that sums up to B of I plus 1 minus B of I, right? So how do you do these partitions? If you do a knapsack, so let's say you don't know the partition till now, okay? You don't know the partition till now. You keep doing a knapsack here. You go this way, right? So knowing knapsack is kind of a prerequisite here. So if you do know the knapsack, so you know what it means to like iterate through this array while doing the knapsack, right? At some point, let's say here, you will find b of 1 minus b of 0. From here on out, you don't really need to find b of 1 minus b of 0 anymore. You already found it, right? From here on out, you can just partition here and just go forward. B of 2 minus b of 1. Now from here, you try to find b of 2 minus b of 1. Once you find that, you will try to find b of 3 minus b of 2. And if b of 3 does not exist, the answer is already yes. In the end, if you don't find that specific sum that you were looking for, the answer will be no. And if you do find the sum, the answer will be yes. So what will be the complexity? Does it change? So you're kind of greedily partitioning. As soon as you find b1 minus b0 as a subsequent sum in Z, you do not look, you partition it there only. So it's a greedy partitioning, right? So this problem kind of covers both greedy and dynamic programming and some ad hoc kind of observations that you need to look through. So the complexity doesn't really change. So the overall complexity remains at O of max into M divided by 32 because of the bit sets. So hopefully this solution is clear, right? We'll now discuss the code for this solution. This is actually the setter's solution, right? No, this is the tester's solution that I'll be explaining. So it's not as difficult to understand if you already know how to implement 0-1 knapsack using a bit set. After implementing 0-1 knapsack using a bit set, all you need to do is just traverse through the array. Every time you find it, just partition it. In the end, if you do find the sum, the answer is yes. If you don't find the sum, the answer is no. Okay, so this part is just input. Input again. If the size of B is 1, if the size of Z is 1, then the answer is yes. So some corner cases are being handled. So this is the main part of the code, right? This is the main part of the code. And yeah, this is the required sum that you need to find. So REQ is the required sum that you need to find. If that is equal to 0, then you just look for the next same element that you want. If it's less than 0, the answer is, so F is the flag. So in the end, you can see that if F, then yes, otherwise no. So if F is 1, that means the answer is yes. If F is 0, the answer is no. So initially F is 1, right? If REQ is less than 0, what does that mean? We covered this case, right? If the required sum is less than 0, that means that this is a decreasing array. So B is a decreasing array. So we just set F equals 0, answer is no, and break, right? And this is doing the traversing. So this is actually a macro. So this means for I equals 0, I less than M minus 1, I plus plus, right? This macro is defined somewhere up here. Yeah, here you go. Okay, so in case you are confused what it means, if you have been doing competitive programming for a while, you'll know what this means. And yeah, if REQ is positive, only then we look for something. So this is actually the implementation of the 0-1 knapsack. If we do find it, we don't go further, right? Like if you don't find it, like ever, then you set F equals 0. Otherwise, you just partition and move forward, right? So L is actually the left side of the partition from which we start looking. So yeah, R is the value of M, is the size of R, size of Z, sorry. Yeah. So this loop, it checks if L is less than R and if not B of the required sum, right? So yeah, this is implementing the 0 1 knapsack. L is the left side of the new partition that we are looking for. And yeah, you keep doing L++. In the next iteration, the left partition is created by default, right? So pretty simple implementation. It's not very difficult. These parts you can just ignore. This is checking the time and everything. You don't need to print it. So yeah, hopefully you enjoyed this problem, and yeah, I'll be making more editorials now. And yeah, have a good night.